Hey, I know that the bell caught us and we didn't get to do the full rate law problem, so I'm actually going to walk you through the practice exercise on page 585 that's actually part of the sample exercise 14.6. And I'm going to do the whole thing, and so that will give you one more model problem as you're doing your homework tonight. I really want you to be successful. Okay, so if you look, we have this general reaction. We've got reactants to products. And the first thing that you're asked to do is to determine the rate law for the reaction. The way you do that is you start by always writing just the generic rate law form. And so it is always rate equals K, that's a constant, and then you put your first reactant in a bracket. Remember, the bracket means molarity of it. And you're going to raise it to some power. You don't know until you analyze the patterns. So let's just call it, raise it to the X power. And then you're going to multiply that. You could put a multiplying sign there or just keep going because that means multiplying. You have your second reactant and you raise that to some power. If you had a third reactant, you would keep going. If, like the hydrogen peroxide, you only had one reactant, then you would just have one. Okay, so that is what every generic rate law looks like. Now, you cannot assume that these exponents will match the coefficients. Sometimes they do, sometimes they don't. It's really just a coincidence. What we have to do is you need a minimum of 3 experiments, and usually 3 is enough. And you just look at how changing concentration affects the rate. We know, when we were talking before about the graphs, we know that the graphs are a curve. And we know from math that that usually means that there is some kind of exponent. So we know that there's something about exponents going on in rate laws. Okay, so here's how you set it up. I'm going to compare experiment 2 to experiment 1. And so I'm going to write a rate law. The rate for experiment 2 is going to be rate, which is 2.46 times 10 to the negative 3 equals K times NO, 0.1, raised to the X, 0.2 for the hydrogen, raised to the Y. That is experiment 2. Experiment 1, I'm going to do the same thing, but use those numbers. The rate is 1.23 times 10 to the negative 3rd, and I guess I should put in the units, molarity per second, equals K times 0.1 molar. This was a molar up here as well, to the X power. And this is going to be 0.1 molar to the Y power. Let me go ahead and put the molarity in here. Okay, this is the hardest part. Now you basically simplify. If you notice, K over K, it's a constant, that cancels. 0.1 m over 0.1 m, both to the X, they cancel. 0.2 to the Y, 0.1 to the Y, that simplifies to 2 to the Y. Over here, this 2.46 times 10 to the negative 3 divided by 1.23 times 10 to the negative 3, this simplifies to 2. So your math basically ends up being 2 equals 2 to the Y. And now you just do this in your head. You solve for the exponent. 2 to the what power is 2? Well, the answer is 1. The nice thing is these exponents are either going to be a 0, a 1, or a 2. Every once in a while they might be a 3, but they're nice, even whole numbers, so it'll be easy for you to guess.